I will begin with a word of prayer. Ahem. 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 Heavenly Father, we thank you for this day. We thank you for the weekend just completed. Just ask you to bless this week, this semester. Just help us to glorify you, what we do this week, Lord. In your name I pray. Amen. So, guys, you got questions? Ladies first. Yeah?
I'm just kind of confused on it because ace of 1 is 1. So, like, you're given ace of n plus 1, but n can't equal 0.
Ace of n plus 1 is what?
N over n plus 1 times ace of n.
And then what's the question? So if we do not understand what the question is, then the question is hard to answer. It's the limit. Find the limit for that thing. So what do you guys think? Well, first of all, can you describe in words what's going on here? What kind of problem is this? The sequence is defined what? Recursively. So how do we solve recursively defined sequence of the limit of a recursively defined sequence? To my mind, there are kind of two paths you can go down. The one path is to mess around with it long enough that you can see the formula for the thing, right? One possibility. And then if you can find the formula and the formula is not too bad, then you can just straight calculate the limit from the formula. The other possibility is we're supposed to use the bounded monotonic sequence theorem. Well, there's the third possibility, which is the thing blows up, right? Maybe you can see that ace of n goes to doesn't go to 0 as n goes to infinity. In which case, game over. It's divergent. Wait a minute. Excuse me. We're talking about a what? Sequence. So what did I just say? I said nonsense. That's what I said. So nth term test is for what? Series. Right. We're talking at the moment about sequence. Yes. So I'm staring at the problem 60. So part A, by applying the bounded monotonic sequence theorem, and by part B, calculating the explicit formula and recursively defined sequence. Yeah. So, where are you stuck?
So when I was trying to find, like, I was looking at the terms, and I was confused because it says for n bigger than or equal to 1, and ace of 1 is 1.
Uh-huh.
So then that means n is equal to 0. It's ace of 1.
Well, no. This formula is for n greater than or equal to 1. This is not part of that pattern.
Oh.
That's the fundamental truth which generates all the rest of them. Like ace of 2. Yeah?
So when you're making your formula, should it be from when n equals 1 to infinity, and just ignore ace of 1 is 1?
No, ace of 1 is 1. That has to be given to you. Ace of 1 is not covered by that formula. But you need to know that ace of 1 is 1 in order to calculate ace of 2, right? Like ace of 2.
No, yeah.
Oh, we're not saying different things?
No. I'm just a little confused.
So like starting at 2, I link back to 1, but 1's already given, right? So like ace of 2 is 1/2 times 1, which is of course 1/2, right?
Yeah.
Uh-huh.
and like the formula for it. But like to get 1 as like the first term when you write out the terms, you have to plug in 0 for n.
But you don't get 1 from plugging anything into the formula. 1 is given to you. A sub 1 is defined to be 1.
So
This,
when you write out your sequence, you just put 1.
this is a definition. So this language, when we define a recursively defined sequence, like the typical language which is used is here's the recursive language, and here's the starting point for the recursion. So like the Fibonacci sequence, right? Fibonacci would be something like this, right? A sub n is equal to a sub n minus 1 plus a sub n minus 2, where a1 equals to 1, a2 equals to 1, and but so like this is for what? For n greater than or equal to 3. So like for the Fibonacci, I have to give you that a sub 1 is 1, a sub 2 is 1, and then starting at a sub 3, the recursion takes over. But that recursive formula doesn't even, like you said, it doesn't even make sense when I put n equals to 1 or 2, because then I'd have like minus 1 or minus 2 on the other side, which I'm not even defining.
So if you were to write out your term of a sub n would your first number that you write be 1/2, or would you just write 1?
In problem 60, it starts at 1. It's 1 and then a half. N equals 1 gives me 1. N equals 2 gives me a half. There's nothing to show for 1. A sub 1 is given to be 1. You can't prove that. It's given to you.
You only plug in 1 for n.
You don't. That formula is only true. Okay, so this is n plus 1.
Yeah. So if you plug in 1 as n, it would be a sub 2.
Right.
That'd be 1/2. So when n is
2, a is 1/2. A sub 2 is 1/2. Oh, my internet's still not connected. I know you guys are all waiting with bated breath for the excitement, which is top hat. I'm still waiting, personally. So for part A, how would you do this? You have to show that the sequence is monotonic, right? And bounded? So, you gotta think about how to do that. Are there other questions? Yeah. Oh, sorry. 60. Were you also wondering about 62? No? What was your one about? 79. All right. 62, let me look at that one. Top hat still hasn't loaded, in case you're wondering. I'm going to start over again. Problem 62, problem 62 is essentially just to derive the geometric series, yeah? Yeah. You're like, well, didn't you do that in class? Couldn't we just copy down what we wrote from our notes in class? Yes. That is the point of that problem, but I want you to take ownership of that for yourself. Yep. Was that the question? The follow up to that was that basically all of the 50s questions? Let's see here. Well, let's see here. Let's talk about that. Well, problem 52 is to state the definition of series. So I hope you can do that. Problem 51 is to state the definition of sequence. So I hope you can do that. Problem 53, when did I do problem 53 in class? Quote unquote in class. Put some quotes around that, because I didn't really do it in this classroom. Where did I do it? In the posted video from the snow day. Yes, 53 is essentially proved there. Problem 54, did I do that in the snow day? I can't remember when I did that. But what is problem 54? Nth term test. That's right. Yes. So problem 54, you got to remember the key to problem 54 is to notice that did you guys ever think about how do we actually define say the sum k equals 1 to n of a sub k? How do we define that? I don't know. You're not. Your neighbor may not like this. Is it? No, I don't know if I ever said this in class. I mean, I think I have. And that's so the sum the nth partial sum is you can define recursively in terms of the n minus 1th partial sum. See this? So I can define like this, and what's the sum k equals 1 to 1? A sub 1. So this actually is this is for this one. It's for n greater than or equal to 2. And this starts the recursion. Yeah. Well, but the point here was just that a sub n is equal to Sn minus Sn minus 1. Recursion is when we define the next step in the sequence in terms of previous steps. So it's like a for loop in programming, right? Kind of. You computer science people, what should I say? A recursion's like recursion, maybe? That seems kind of circular. But that's kind of what recursion is. I should stop this nonsense. Look, so problem 54, however you see it, whether you see it formally like I've written it here, the way I did this when I did this, I can't remember if did I do this actually in class or did I do it in the video? I think in class, I didn't write it in terms of this. What did I do? I just did like plus ... notation and argued this, right? But this is you really get right down to it, it's the definition of the finite sum that gives you this. But anyway, if this goes to L and that goes to L, in other words, if the series is convergent, what do we have? That the nth partial sum goes to? Not 0, but a finite limiting value, L. If you let n go to infinity, how about n minus 1? Does it still go to infinity? Yeah, right. So if these both go to L as n goes to infinity, then what does a sub n go to? 0. That's the nth term test. And that's also essentially the solution to problem 54. All right, I think that answers the question that you guys asked and all of the related questions about, am I really just asking you to repeat what I've done in class? Yes, I am. But I want you to understand it. Because all too often, calculus students have this habit of tuning me out when I do a proof. You shouldn't do that. If I'm doing a proof in here, odds are it's illustrative of some concept that I want you to understand the nuts and bolts of. Okay, so problem 79? Was that the question? Oh, goodness. Whoa. Wow. So now, why are you doing that to me? 2 to the k. 2 to the k times k factorial over what? K to the k. Sum k equals 1 to infinity. Oops. So the question is how to decide whether that converges or diverges. What do you guys think? Maybe we should try something slightly simpler. Let's try the sum n to the n over n factorial. See if we can come to terms with that one. What do you guys think about this one? Is that another homework problem? What's that? It is? Or it's like it? See, I guess we could try the ratio test, right? We could try ratio test. What would happen? First of all, I don't think the root test is helpful here because of the factorial. I could be wrong about that. We could also try the root test, but let's try the ratio test. Here, a sub n is n to the n over n factorial. So if we do a sub n plus 1 over a sub n, what would we like to happen here? We would like for this limit to come out to anything except for what? What's that? 1. Yeah, 1 es no bueno. Because that's the case that the ratio test is inconclusive. And we do not like inconclusive, because inconclusive means that we conclusively have to do more work. So this is, a standard trick, multiply by the reciprocal, right? That's division. And then I need to do some algebra here, and so it's not too bad, actually. This is n plus 1 times n plus 1 to the n times n factorial divided by n plus 1 times n factorial times n to the n. So do you understand what I did? If we have the n plus 1th power, I can rewrite it as the nth power times just one copy of what we're raising to the n plus 1 power, which in this case happens to be n plus 1. So let me use some color coding to try to explain to you what it is I just did here. So like this one, I've expanded like that, right? And remember, n factorial was defined what? Recursively. So this is the recursive definition of n factorial. We can rewrite it as n plus 1. I mean, n plus 1 factorial is n plus 1 times n factorial. This is an identity for the factorial, essentially the definition of it. And once you do that, there's some nice cancellations, isn't there? Like the n factorials are canceling. What are we left with? N plus 1 to the n over n to the n. Aha! Well, now I have things of the same power, right? So I can use laws of exponents to combine them into a single fraction. N plus 1 over n to the n. Yeah. And then I can use, oh man, oh, well, this is the worst. Well, is it the worst though? As n goes to infinity, what happens there? One to the what? 1 to the infinity, which is not 1. This is an improper, this is an indeterminate form, right? So what's the limit as n goes to infinity of 1 plus 1 over n to the n? Do you guys remember? Let's see here. So the limit, I'll do it over here then. Limit as n goes to infinity of 1 plus 1 over n to the n is equal to the exponential of the natural log of the limit n goes to infinity of 1 plus 1 over n to the n, which is the exponential of the limit as n goes to infinity of the natural log of 1 plus 1 over n to the n, which is equal to the exponential of the limit as n goes to infinity of n times the natural log of 1 plus 1 over n, which, I'm tired of writing all this. I'm going to call this thing star. Focus my attention on star. Star is equal to the limit as n goes to infinity of the natural log of 1 plus 1 over n over 1 over n by algebra. And then I can apply L'Hopital's rule after having extended n continuously. Right, because I'm looking at type 0 over 0, right? Having done so, what do I get? The limit as n goes to infinity of 1 over 1 plus 1 over n times minus 1 over n squared, all divided by minus 1 over n squared. Yay, the minus 1 over n squareds cancel. Cha-cha. Leaving me the limit as n goes to infinity of 1 over 1 plus 1 over n, which goes to 1 over 1 plus 0, otherwise known as 1. So star is 1. A star is 1. Exponential of 1, aka e. So in fact, this a sub n plus 1 over a sub n goes to e. So what do we get to say about this series? Now you guys told me you learned L'Hopital's rule in Calculus 1, so this should not be news to you. I mean, we had x going to infinity rather than n, but the patterns should be the same. This is one of the fundamental indeterminate power limits that you should have been taught. If you don't remember it, it's okay, but you need to learn it again. Or relearn it, something. Now, I don't really expect you to go through all this. All right? Like, this is a known limit. If we see 1 plus 1 over n to the n, the fact that that goes to e, that is known to us from Calculus 1 at this stage in our existence. All right? I mean, you should be able to reproduce these sort of arguments, but in the heat of battle in a Calc 2 test, I don't really expect it. I expect you to know this, though. Okay, so then what? What's the conclusion? Right, therefore, the sum n equals 1 to infinity of n to the n over n factorial diverges by ratio test. What did we call the ratio? I think we called it rho, right? Was it lambda? It was lambda. Thank you, guys. With lambda greater than 1. Somebody else asked me a great question in office hours. Asked me, like, what about the root test? What if the rho is larger than, if the rho was larger than 1, we had it diverged. The question was, is infinity included in that? What if rho works out to infinity? Does the root test say that the series is divergent? The answer is yes. Whether or not the book says it, it's true. If the root test works out to infinity, it's a divergent series. That's enough to prove that the nth term doesn't go to 0. You can work that out. There's a related example, right? What if we turn the tables? Without hardly any additional calculation, what if I just flip the term over? What if I just turn it over? What happens? N over n to the n. So now a sub n is what? N factorial over n to the n. And a to the n plus 1 over a sub n, by the algebra I just did, turned over, is what? It's 1 over 1 plus 1 over n to the n, which goes to 1 over e equals to lambda less than 1. Therefore, S is convergent by ratio test. There's a larger intuition to sort of garner from this problem, which is what? Yeah. Don't make it harder than it needs to be. Choose the easiest one. This is always a universal life goal for us in Calculus 2, yes? But more specific to this problem, what are we learning? Yeah.
N to the n is like larger than n factorial.
Right. In a battle of n to the n versus n factorial, bet on n to the n. N to the n is the bully to n factorial, right? It will put it in its place. Not that we encourage bullying in here, of course, or cyberbullying. You know, we're against that, right? Are you guys cyberbullies? No? You bully in real life? No? I don't know. So I don't know. What about this problem 79? What do you guys think? So now this is like two people standing up to a bully, right? You got like 2 to the k and k factorial. They're both there, and they're waging war against k to the k. Who will win? I don't know. I tend to think it converges because k to the k is like way bigger than k factorial. Why is that? Oh, but we had another problem which is related to the 2 to the k over k factorial. Maybe that's useful. I don't know. What was that other problem? promised I'd talk to you guys about this one at some point. Let's do it. Because we haven't done an argument quite like this in class yet. But you probably could, I mean, it's not completely divorced from things we've done. It's just, you got to have the courage that you can do it. So the question is to show that 2 to the n over n factorial is less than or equal to 4 over n. Or how about we try 3 to the n over n factorial. See if we can make that less than or equal to something. Let's work on a related problem that's almost the same but a little bit different. So I want to give you the opportunity to derive this for yourself, okay? This is problem 70. So I want to try to bound 3 to the n over n factorial. So let's just write it out and try to gain a sense of what that looks like. So what does 3 to the n over n factorial look like? It's 3 times 3 times 3 times 3 times, well, you get the idea, times 3 times 3 times 3. And then downstairs I've got what? I've got n minus 1, n minus 2. It is 2 to the n. I'm working a related but different problem. N minus 3, 3 times 2 times 1. But if you understand the steps I'm doing here, problem 70 should be a breeze. So the question is, we want to get rid of the factorial, right? I mean, I want to put this is, less than or equal to like something over n maybe. That would be cool if I could do that. How am I going to get to, how do I get rid of this mess down here and just, how to remove these? To make the fraction, what? Larger, I must do what? Make the denominator smaller. So it would be nice. I mean, first of all, I don't really care. This stuff over here, like leave it alone, whatever. This over here, I'm just going to leave that alone, whatever. I'm going to focus my attention on the middle, right? I want to get rid of that. Oh, I guess I can probably do this, right? Since those cancel, whatever. So I need 3 to be what as it compares to n minus 1? I need 3 to be what as it compares to n minus 2? I want 3 over n minus 1 to be what? if I had 3 over n minus 1 less than 1, would that make 3 over n minus 2 less than 1? I mean, isn't this less? We're thinking about n pretty large here, okay, guys? Because n minus 2 is what? Wait a minute. Is it that way? Uh-oh. That would make... Oh, yeah, that's not going to work, is it? Oopsie. I mean, that's not true. See, maybe I need to write out a little bit more. Let's see here. So I should probably like break it in the middle with a specific thing. Let's say until I get to ... n minus j, let's say, and then 3 times 2 times 1, and then there's still a 3 up here. 3 times 2 times 3 times 3 times 3, right? So then how does, in this thing I just wrote, what's j equal to? I mean, n minus j should be equal to what? If this pattern is right. 4, right? Yeah, yeah. And for us even to be looking at this, what are we assuming about n? To even consider this pattern as we are, for it to make sense, what am I assuming about n? It's at least what? I think 5, yeah? I mean, 5, I don't feel, I think if it's at 5, I've got this one, I've got at least one middle term, and I've got these 3 terms over here, and that's... So what do I want? I want 3 over n minus j to be what? To be less than 1. Because if I could do that, if that were the case, then likewise, we'd have what? 1 over n minus 1, 1 over n minus 2, 1 over n minus 3, 1 over n minus j. Right? You know, all these would be less than 1. I need to put 3's in the numerator, obviously, right? So I was trying to start this story at the left, but that didn't work out. So I really need to start this over here, because then if I have that's less than 1, then I get all of these are less than 1. In case you're not following me, let me actually put it down for like 6. 3 to the 6 over 6 factorial is 3 times 3 times 3 times 3 times 3 times 3 over 6 times 5 times 4 times 3 times 2 times 1. So I'm focusing here on the middle. These guys. So I'm saying 3/4 is greater than 3/5, If in other words, if this one's less than 1, it follows that that one's less than 1. So all I need is what? I need 3 over n minus j to be less than 1. So how do I get that? Three is less than n minus j, which says what? This j, what could it be? It's some number, what, between 0 and n, right? So it should be clear. So if n is equal to 4 plus j, j is. So can anybody complete the thought here for me? What should I assume about n in order to make the middle things? I mean, what I'm trying to argue is if you fill in the blank, then given what we've just shown above, 3 to the n over n factorial is less than or equal to 3 over n times 3 times 3 times 3 over 3 times 2 times 1, also known as 27. Oh, also known as 3's cancel. I think 3 over n. I need n to be large enough so that 3 over n minus j is less than 1. How big does n have to be to make that happen? Where j is what? Oh, I mean, this is 3/4, isn't it? So do we need any condition on n? Not really, right? What do we just need? If we need n is greater than or equal to 5. If n is greater than or equal to 5, then what I've written, this pattern, to recap, if n is greater than or equal to 5, I can write this expression. Then this is 3/4, right? So the point is that all of this in the middle is less than 1. So this is greater than, if I haven't messed up the number 3's, 3 to the 4th over, how did I, oh, is this right? No. What should I have there? Looks like 27 over 2n, yeah? The 2's, this 2 is still there, right? So I hope some of you saw that when I was about, like 60% of the way through it. It takes me for a while to like shake myself loose of my various misconceptions about how to process that kind of fraction. But once you see things clearly, but you notice it's if n is greater than or equal to 5, I can write this, right? And then once I can write that, I get this estimate. What's that show? That shows that 3 to the n over n factorial is less than or equal to 27 over 2n, which would be useful if I wanted to do what? Show that this is going to 0. It would not be terribly useful as a direct comparison test, though, would it? But if you wanted to show that this series, the corresponding series here, sum n equals, say, 0 to infinity of 3 to the n over n factorial is converged, what should you probably use? Just ratio test. Ratio test will do this one, right? You see there are other estimates. You could not throw away one of these, and you could bound it by like a 1 over n squared term, right? But anyway, it may be that this kind of calculation in a comparison test is what you need to, I don't know. Problem 79, you'll have to think about. So, listen, I'll shut up. Our time is up, so